In episode 66, titled Feature Reshaping, Ratios, Aggregations, and Pivoting Concepts, the focus is on reshaping features to express behavior, not raw measurements, because raw fields often describe events and attributes in forms that models cannot use effectively without structure. Many real systems generate data as logs, transactions, and clicks, and those records are meaningful only when you summarize them into signals about frequency, intensity, and change over time. The exam cares because feature reshaping is where you turn raw telemetry into decision-ready evidence, and scenario questions frequently test whether you can recognize that the right representation matters more than the fanciest algorithm. In practice, reshaping is also where you reduce confounding from exposure differences, align features to decision horizons, and improve interpretability by making signals map to understandable behaviors. The goal is to build features that tell a story about what the entity did, not just what was recorded. When you learn this mindset, you stop treating feature creation as decoration and start treating it as measurement design. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Ratios are one of the simplest reshaping tools because they compare scale, turning two raw quantities into a single relative measure that often aligns better with risk and behavior. Spend per visit is more informative than spend alone when the number of visits varies widely because it distinguishes high spend due to frequent visits from high spend per interaction. Errors per hour is more informative than raw error count when observation windows differ because it normalizes by time and makes rates comparable across entities. Ratios also reduce the influence of size and volume, which is important in systems where large customers, heavy users, or high-traffic devices would otherwise dominate every model simply because they generate more data. The exam expects you to recognize when a raw count is confounded by exposure and when a ratio would better represent intensity. When you narrate ratios, you are saying that behavior is often about efficiency and intensity, not just about totals. Rates are closely related, and they normalize counts across exposure or time windows so that comparisons are fair across entities with different opportunity levels. A count of incidents is not comparable across systems with different usage levels unless you account for exposure, such as incidents per 1,000 sessions or incidents per device day. A count of clicks is not comparable across users with different activity unless you account for opportunities, such as clicks per email received. Rates are also useful because many outcomes and risks scale with opportunity, meaning you should model the probability per opportunity rather than the raw total. The exam often uses this logic to test whether you will interpret raw counts as risk when they may simply reflect volume, and the correct response is to normalize by an exposure denominator. A well-chosen rate can turn noisy raw counts into a stable signal that generalizes across segments and time. When you use rates thoughtfully, you are building features that reflect behavior relative to opportunity rather than absolute volume. Aggregation is the workhorse of behavioral feature engineering because it turns event streams into summaries that models can consume, such as totals, means, maxima, and recency. Totals capture overall volume, means capture typical intensity, maxima capture worst-case behavior, and recency captures how recently something happened, which is often more predictive than lifetime history. Aggregations can also include variability measures, such as how spread out behavior is, but even basic summaries can dramatically improve model signal because they align with how decisions are made. In many scenarios, you are not predicting from individual events. You are predicting from what a user, device, or account has been doing recently and consistently. The exam expects you to recognize that raw logs often need to be rolled up to an entity level, because the unit of prediction is typically an entity, not an event. When you narrate aggregation, you are describing the conversion from raw sequence to meaningful summary that captures behavior patterns. Window length is a critical design choice because aggregation is only meaningful when it matches the decision horizon and the system's seasonality. A short window captures recent changes and rapid shifts, which is valuable for operational detection, but it can be noisy and sensitive to bursts. A long window captures stable behavior and reduces noise, which is valuable for strategic scoring and long-term risk, but it can dilute sudden changes that matter for immediate response. Seasonality also matters because windows should capture full cycles when you want fair comparisons, such as using weekly windows to reflect day-of-week patterns or monthly windows to reflect billing cycles. The exam often hints at this through scenario constraints like daily review process or weekly reporting cadence, and the correct reasoning is to align aggregation windows to how the output will be used. If you choose the wrong window, you can create features that either react too slowly or oscillate too much, undermining both performance and trust. When you justify window length, you demonstrate that feature engineering is tied to operational rhythm, not arbitrary time slicing. Pivoting is a conceptual reshaping approach that turns categories into consistent feature slots, allowing you to represent category-specific behavior in a structured, model-friendly way. In practice, pivoting means taking a variable like event type and creating separate features for each type's count, rate, or recency, so each category becomes its own column. This can be powerful because it preserves information about which categories occurred and how often, rather than collapsing all categories into a single mixed count. Pivoting also supports interpretability because each feature corresponds to a recognizable category, such as a specific error class or activity type. The exam expects you to understand that pivoting creates a consistent schema across records, which models need, but it also expands dimensionality, which must be managed. When you narrate pivoting, you are describing how to convert a long event list into a wide behavioral fingerprint that can be compared across entities.
Target leakage is a constant risk in aggregation because it is easy to accidentally include future information when building summaries, especially in time-ordered systems.
Leakage can happen if you aggregate events over a window that extends beyond the prediction time, or if you compute totals using the entire dataset without restricting to what would have been known at the decision point. It can also happen when an event is generated only because the outcome occurred, such as a remediation action logged after an incident, and including it in a summary would reveal the target indirectly. The exam frequently tests leakage in time-based features because it is a subtle but devastating validity failure, and the correct posture is to enforce strict cutoff times for aggregation. A safe mental model is that every aggregated feature should be computable at the moment you would actually score the entity, using only past and present information. When you narrate this, you show that you understand aggregation is part of the causal timeline, not a free computation. Missing categories in pivots require explicit handling because absence can mean either true zero or unknown coverage, and mixing those meanings creates bias. If an entity truly had zero events of a type, encoding that as zero is appropriate and informative. If the data source did not capture that event type for this entity, encoding as 0 would be misleading because the absence reflects measurement gap rather than behavior. This is why unknown flags or coverage indicators can be important, especially when data comes from multiple sources with uneven instrumentation. The exam often tests whether you will treat missing as 0 without thinking, and the correct reasoning is to distinguish true absence from missingness due to collection limitations. Handling missing categories consistently also improves model stability because it prevents random sparsity patterns from being interpreted as meaningful signals. When you address this carefully, you are treating representation as part of measurement accuracy, not just as a modeling convenience. Scenario practice helps make reshaping concrete because the right reshape depends on whether you are modeling customers, devices, or sessions and what decision the output supports. For a customer scenario, ratios like spend per visit and rates like support tickets per month can normalize for activity level and highlight intensity. For a device scenario, rates like errors per hour and recency of critical faults can capture reliability trends that matter for maintenance decisions. For a session scenario, aggregations like maximum latency, average latency, and recent failures in the last window can capture immediate experience risk and support real-time triage. In each case, pivoting can add category-specific fingerprints, such as counts by error type or counts by action type, as long as you manage dimensionality and consistency. The exam expects you to choose reshapes that align with unit of analysis and decision horizon rather than applying the same recipe everywhere. When you narrate these choices, you show that feature engineering is contextual. It reflects the entity, the timeline, and the decision. Reshaped features should be validated for lift, stability, and interpretability, because reshaping can improve one dimension while harming another if done carelessly. Lift is whether the new features improve predictive performance or causal signal relative to baselines, and it should be measured on held-out data to avoid chasing noise. Stability is whether the model's behavior and feature importance remain consistent across resamples, time windows, and segments, because unstable gains are usually overfitting. Interpretability is whether the new features tell a coherent story that stakeholders can understand and act on, because a feature that improves metrics but cannot be explained may create governance friction. The exam often rewards answers that include evaluation discipline because feature reshaping is powerful enough to create false improvements if it leaks information or explodes sparsity. When you validate across these dimensions, you show that you treat reshaping as a controlled intervention rather than as unlimited tinkering. Feature explosion is a real risk, especially with pivoting, and managing it often requires grouping rare categories before pivoting so that you do not create thousands of sparse columns with little support. Grouping can mean consolidating rare labels into an other category or into semantically meaningful groups, such as grouping similar error codes or similar event types. This reduces dimensionality, improves statistical support per feature, and reduces the chance the model memorizes rare categories that will not generalize. It also improves maintainability because pipelines and models are less sensitive to new categories appearing over time. The exam expects you to recognize that pivoting is not free. It creates a larger feature space that must be managed with evidence and constraints. When you manage feature explosion deliberately, you preserve the value of category-specific information without turning the dataset into an unstable, sparse matrix. Documentation of derived feature logic and window definitions is essential for reproducibility because reshaped features are not raw facts. They are computed representations that depend on choices. Documentation should state how each ratio is computed, what denominators are used, how zero denominators are handled, what time windows apply, how recency is defined, and how categories were grouped before pivoting. It should also specify the cutoff time for aggregation to avoid leakage and should describe how missing categories are represented. The exam treats this as governance because derived features can encode policy and can materially affect decisions, so they must be auditable. Documentation also supports future maintenance because when performance shifts, you can determine whether a drift in behavior or a change in computation caused the change. When you document reshaping properly, you turn feature engineering into a disciplined, repeatable process rather than a collection of undocumented tricks. A helpful anchor memory is reshape highlights patterns, raw data hides them. Raw data is often event-level and messy, and the patterns that matter are usually about rates, recency, and composition across time rather than single events. Reshaping highlights those patterns by converting raw streams into stable summaries and normalized measures that make entities comparable. The anchor also reminds you that reshaping is not optional in many real datasets because models need consistent, comparable features, and raw logs often do not provide that. On the exam, this anchor helps you choose feature engineering approaches over algorithm changes when the scenario implies that structure, not model family, is the bottleneck. When you apply the anchor, you look for ways to express behavior more directly, which often yields larger gains than switching from one model type to another. To conclude episode 66, choose one reshape and describe its intended meaning, because meaning is what makes a derived feature useful and defensible. Suppose you create a feature like errors per hour for a device over a trailing 7-day window, which is a rate that normalizes error count by observation time and captures reliability intensity. Its intended meaning is that a higher value reflects a device experiencing frequent failures relative to its time in service, which is more actionable than raw error count when devices have different uptime and usage. You would ensure the 7-day window matches the decision cadence, such as weekly maintenance planning, and you would enforce a strict cutoff so the rate uses only data available before the decision point. You would also document how you handle missing uptime data and how you treat devices with 0 hours to avoid division artifacts. This reshape is valuable because it turns raw events into a comparable behavioral signal that supports stable modeling and clear operational interpretation. Thanks for listening. For more audio courses, daily newsletters, and more, please visit bare-metal-cyber.com.